Hey, welcome back. So this will be episode 2 of my series on how to backdoor or Trojan a Linux system. So essentially, what I mean by that is if someone hacks your computer or gets unauthorized access to your computer and has root. Normally, what they're going to do is they're going to try to hide themselves from you. They want to maintain root. They want to run their own programs, but they don't want you to see their programs running. So again, for example, if I'm a hacker and I get into your system, maybe I want to use it to run, a DDoS client. So, I'll upload my tools, I'll run the client, and but you can see it in the process list. So if you're the administrator, it's pretty obvious that someone's got access to your system. Now, in my first episode in this series, I showed you how to download the source code to PS and make changes to the source, recompile it, and then copy it over top the system binary, the system PS binary, with your changes, and ultimately your changes actually hid the DDoS net process, or any process that you wanted for that matter. Now, we looked at the weakness of that was, the administrator could use MD5 sum on the original binary, get the hash, and he could save that somewhere, and then he could run an MD5 sum every day to check if any files have been modified. If the hash generated by MD5 sum changes, he knows that the binary's been modified. So it's a very easy to detect backdoor Trojan. It's very noisy, Some other changes as well is we noticed there was a difference in the file size. There's a difference in the access time, modification time. Obviously, those can be all changed, but the file size can't. So again, it's really easy to detect that. One thing to note is, back in like the mid 90s, 95, 96, 97, most people, like most, you want to call them script kids or crackers or hackers, who were actually, hacking systems, that's what they used to actually backdoor a system. They used, something called LRK, Linux rootkit, and all this was a collection of Trojan binaries. So they would Trojan PS to hide processes, it would Trojan W to hide who's logged in, it would Trojan LS to hide files. It had replacements for all those binaries. Now back then, obviously, people didn't take security as important as they do today. Obviously, nowadays, if you modify those binaries, more than likely on a system that has anybody administrating it that's got a clue, they're gonna find out pretty quickly. So around late 97, 98, 99, people started developing other rootkits. What I'm going to show you today is something called LD preload, and later on we'll get into kernel module rootkit, which is probably the stealthiest and the one that's still used today. LD preload is a userland rootkit, and what it does, it takes advantage of the Linux LD preload feature. Now, I went over this in one of my reverse engineering tutorials, and just so you know, LD preload, what that does is it allows you to link in your own shared library before any of the library gets loaded in any file on the system. So when any binary runs, it will actually load our shared library first. Now, the beauty of this is that we can then, we can take over libc functions just by, creating our own versions of them, and then what we would end up doing is we want to check the arguments passed to those libc functions like open or read directory, and inspect the arguments and see if it has something, that we want to hide, like our process descriptor, process ID, process name, file name, what have you. And if it does, then we'll take the required action to actually return a false value so that it's not returned to the user, so the administrator can't see those files or those processes. So I'm going to show you that today. What this does is it doesn't actually modify any binaries. We basically just inject our own code, write our own code, and put that in the system without modifying any binaries. So let's do that real quick. It's very basic. I'm not going to get into an actual rootkit. Just going to show you how to actually hide processes and files and what have you with your own code. But this is not something that's really production, worthy. You'll have to actually go and develop your own. Again, though, remember, to learn this stuff, you want to learn how people do it so that you know what to look out for. You don't actually want to go out and do this kind of thing, because nowadays you get caught, unauthorized access to a computer system. You're looking at like years in jail. Just not worth it. So let's call it rk.c, rootkit.c. First thing I'm going to do, what I'm going to do is, actually real quick, if you remember whenever we looked at hiding processes, I explained the /proc file interface. So /proc basically contains all your process IDs and their directories. And inside those directories, they have all the information for each process. So if we look at our DDoSnet, it's 23977. So there should be a corresponding directory entry in /proc for 23977. And there is, and in here you can see there's a bunch of information about your process that's running. If you look at the command line, it shows the actual command that was run. So knowing that a process is just literally a file in the /proc interface file system, we can actually intercept open calls, look for that directory name, that file name, and if it's equal to that, we can return some kind of false value so that it's not going to actually get access to that process. All right, so again, so what we're looking for, we're gonna try to intercept calls to /proc /23977, because that's the directory that's going to contain all the information regarding this process. So first thing we're going to do is we're going to actually write our own open call. So it's going to be these same exact arguments as the libc open. So it's going to be const ** file name, and then it has flags and it's mode t mode. Obviously, if we have to, we can check right here. Check it out, and yeah, that's what it is. And go back here. We'll close this for now. Close that. So now the code's gonna be very similar to what the binary Trojan was. In this case, though, we're actually just gonna do a string compare. So I'm just gonna go with not string compare. Our file name to /proc /23977, because remember, it's going to be opening a file inside this directory. We don't know which file. It could be /command line to get the command line. It could be some kind of memory map stuff. I mean, who knows? There's a lot of information in there. Most of it I have no idea what it's about. But we just want to know if it's opening something in that directory. So we'll just go like this. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to compare the first 11 characters in our file name to /proc 23977. And if it returns 0, we know that it's a match. And at that point, we want to hide it. So let's look at open again. We want the return value. The return value upon successful completion. So that's not what we want. We don't want it to be successful. We want it to be, failure. So otherwise, these functions shall return a -1 and set error node to indicate the error. I don't know why I didn't say negative. I don't know what's wrong with my types. But anyways, to indicate the error, if -1 is returned, no file shall be created or modified. So we've got to set error no. If you don't set error no, the program's trying to read these files won't give you the right error information. It'll be clue to the system administrator that something is wrong. If you set the correct error, so in this case we're going to set no entry, which essentially means that the file doesn't exist. So we'll get the actual correct error message saying that the file doesn't exist. If you don't set error no, you might get some kind of e-access error or something like that. So error no, it's a global variable defined in error_no.h. We're going to set the no entry and then return -1. let me just include some header files that we're missing right now. So I want to include sysstat.h. That's for the mode T type. Then we want to include airno.h, so we can access the airno and the enoent define, and string.h for string compare, and we're going to include dlfn.h. So because now what we have to do, because I mean obviously right now if we just leave it like this, then when someone tries to open a file in the system, nothing's going to happen. It's going to go to our open file. It's going to check to see if it's, one of the files we want to hide. If it is, it performs correctly. But any other file, it doesn't actually open it. It doesn't return open this file descriptor. What we've got to actually do is we've got to call the original open, the libc open. Now to do that, there's actually an API interface under Linux called dlopen. And what this does, especially if you're familiar with Windows and get proc address, basically it's the same thing. All it does is it will give you the address. Well, first dlopen actually gives you the address. It'll open up a shared object, so like libc, and then within libc we can find symbols with the dlsim call. So let me show you that real quick. Let's just go void start p equal dlopen/lib/lib, whoops, libc.so.6. So we're going to open up libc, and the flag is going to be rtld lazy. You can read what the flags further down, right there. Now, that returns a pointer to the libc shared object, and now we want to actually look at dlsim. So dlsim will find a symbol within that object. So now what we're going to do is we're going to basically find the address where the function open is, and then we're going to just basically call that function. So I'm going to create what's called a function pointer. So I mean, it's just defining the open system call, but it's a pointer to it. So we're going to call it p_open. And then the arguments, so it's going to be a const char int mode t equals dlsim. My L button doesn't work. And then it's going to be the handle to the shared object we're looking under, which is going to be p, and then it's going to be what we're looking for, which is open. So what that'll do is that'll return the address into a function pointer that we declared of where open is, and then we can actually just call that function. Actually, what I'm going to do is return it with the arguments passed in to us. So now what happens is, first thing we do is we check and see, is it trying to read anything but the process that we're trying to hide? If it is, we set airno to no entry, and we return -1. So we're saying basically that file doesn't exist. Even though we know it does, we're saying it doesn't. So that programs like PS and top won't report it in their output. If it's not that program, any other program, what we're doing is we're basically just going to find the address of the real open, libc open, and then return we're going to call that function, the address that we get from dlsim, and return whatever it returns. So we're just basically doing the call for them at that point. Now what we'll do is we will see if we can compile this. Let me just run PS again. We see our DDoSnet. Let's try to now when you're compiling this, it's a shared object, and we're going to go position independent code, and then what did I call it? rk.c. Might have some errors. I do. It's not what is it? dlfcn function, whatever. Okay. Whoops. Enoent undeclared. I thought I. did I call it? I know equal enote. Oh, I've got an extra n. Okay. Now it should compile. It does. So now it's there. Now again, PS, it shows DDoSnet. Now if I export my LD preload variable and load our rootkit, I run PS, it's hidden. Now one thing to note that I didn't show you is if we try another, now this, again, remember, this shared library is running over all your binaries are linked into this now. So it runs before every binary. So if I run something like touch, test, symbol lookup error, rk.so, undefined symbol DL open. Now why that's happening is because the touch binary doesn't actually use DL open. It's not linked to the library. So in order to fix that, you need to link, when you compile your code, you actually need to link to library DL. So it's something like this, LDL. Oh, let me just first take out the preload. Now I link it to LDL. We'll export our rootkit again. It's still hidden. And now we can touch whatever we want. Now any binary in the system that actually isn't linked in with DL, it doesn't matter because we've linked it into ours. Obviously, you can see if you didn't do that, you'd be found out pretty quick. We can also go PS all users executable grep DDoS, not there. So now you're saying to yourself, I mean, if you're thinking about it, well, how can you get the administrator to run, an export LD preload equal your rootkit? That's obviously not going to happen. So actually, a good thing for us or for hackers or what have you is that you can define a global preloaded library in /etc/ld.so ld preload or no, ld.so.preload. So if I do something like this, it would be /code/ld preload /rk.so to /etc. Oops. ld.so.preload. And now it's hidden. So now it's hidden for the whole system. Now any user is going to have that shared library loaded first. So now if I do like a remove, and now it's not hidden. So that's what you would do. I mean, you would actually just develop your shared library, put it somewhere in the system, and then put the path in /etc/ld.so.preload. So now we basically we Trojan PS or what have you process listing, but we haven't modified any binaries. So it's much better than the first episode of the rootkit, Trojan binaries. However, I mean the obvious, obvious to detect this is if the administrator just used ls to look at, that file ld.so.preload, and it's not there, okay. But if I set it up to be there, so now it's hidden. But if an administrator comes in and he's wants to check to see just if he's backdoored, he'll check it. He'll see right away. Oh wow, what's going on here? And then he'll cat it or what have you, and he'll see exactly where our rootkit is. So that's pretty easy to detect. But remember, we actually can control. We can control the output of ls too. Because ls as well is just running, libc functions that we can take control of, that we can, not overwrite, but write our own versions for. So let's just do that real quick. If I was to do that, we would look at what would actually do. what I normally do is I'll do like an L trace on ls minus L. Oops. LD dot so. Oops. My L button does not work. It does a lot. There's a lot of setting up your terminal and output and stuff for ls. But if you scroll up not too far, you'll see the function. Here's what we need right here. So I mean, it gets a string length of LD a file we're actually looking at. Then it calls an Lstat on it. So that's actually the call that we'd look into backdooring. Whoops. Come on. Just want to check one thing. Yeah, I named it wrong there. Stat should have returned not -1, but my L didn't work as usual. So let me show you that again. We'll grep. That didn't look stupid. Okay, so where is it at? Right here, so you see return 0 because the file is actually there. We saw that when the file wasn't there, when I mistyped it and forgot the L, it returned -1. So common sense tells you all you got to do is backdoor this call here, Lstat, to return -1 if it's trying to find ld_so.preload. So let's do that. Let's see if that will work for us. Now, if you do a man on Lstat, you know, it's not going to work. Or if you go, you know, like this, it's not going to work. Lstat is actually a wrapper call to the stat function. There's actually a bunch of different versions. Lstat, there's fstat. And so what it does is basically, depending what you want to call, Lstat actually Lstat is what gets called, and depending on the version you pass it, it'll call one of these functions, I believe. So we actually have to backdoor Lstat. So for that, return. You know, I googled the actual arguments for Lstat, but it's the same as stat, except it takes a third argument of a version string or int version. So we can go something like this. Oops. Okay. Now, once we're inside of this, we're going to look at the file name. So we're going to do something like if string, actually, if not, string compare to our file name, ld_so.preload. It's going to be the same thing. Error node is going to be enoent. Return -1. Otherwise, we're going to do the exact same thing here. We're just going to get a pointer to the libc shared object file. Let's see, libc. Oh my gosh. Now, also, really, I mean, we shouldn't be doing these calls inside the functions. You know, I should be defining void/p globally, and not making these calls every time. But it's too late now. Doesn't really matter. It's just so you guys can kind of see you know what happens. So now we're going to do a return. Oh no, we're not. Sorry, we gotta actually find the symbol. So to find the symbol, we're going to go like this. Like that. int string star file name struct stat star equals dlsim p, and we want to find Lstat, and then we'll return call the return value of actually calling the function, the libc function, with the arguments passed in by the the calling function. So hopefully that works. I don't know. Real quick, I may have made mistakes. Let's compile it. Now, let's just put it in right there. If we do a PS, we see that we're still hidden there. Let's just do an ls, make sure nothing's broken. Nothing's broken here. Now if I do an ls /etc/ld.so.preload, no such file directory. But if I do an ls minus la let's just do it on the directory itself to get all the files. If you scroll up in here, you'll actually see, oops, it's still there. And look what's happened here. Now, let's unhook it. Actually, just want to oh my gosh. And then I want to go echo, no. I'm gonna just export it and see what happens. Not there. Now see, what's happening is we're not actually returning the stat buff because it's what's happening is it's actually calling a read directory. So if we look here, read directory is being called. It's actually returning that file name, but then when it actually tries to stat it and get the actual file information, what kind of file it is, who owns it, the size of it, it can't get that because we've Trojan the stat function to return -1 for no file. So that's why you're seeing these question marks. Now, what you got to do next is you've actually got to backdoor read directory, so that even when they're listing the whole directory content, where they're actually calling read dir, then LDP won't actually show up. But that's why it's showing up. I knew that it would show up, but I forgot that it stats inside of that read directory call to actually get the information, which is why we're seeing those question marks, which is why it kind of took me for a surprise for a second there. So now, all it is backdooring a read directory. Real quick, this is running super long, but so again, same thing. We're just gonna write our own read directory, exact same arguments. Whoops. So now in here, I'm going to go with struct dirn star, go like that, and then all I'm going to do is I want to go again. Me getting the pointer to libc in every function is stupid. I should get it once and then just check if it's null or not. But again, it's too late now. So let's find libc again. Let me just go like this. and then I'm going to find the symbol for redirectory. This, and then I'm going to do something like this. What did I want to do here? Oops. Now what we have to do is we've got to actually get the directory entry structure. That's what it wants. Return. So what happens is the first time through here, the first time it's called, you know, there's nothing filled in. So we're going to fill in the directory entry structure by going something like this. D entry equals p read directory dirp, and then if d entry, and then if dent. Oops. If string compare, no wait, not copy. What are we looking for? If, blah, blah, blah. Oh yeah, like that. D underscore name, yes. We want to actually see if it's going to be returning 0. Go like this, go like this. So same thing, set errno to eno entry. Oh. Actually here we're not, it doesn't actually, there's no return value. It's not a, you know, negative return value. What happens is it will continuously call redirectory for the next file. So what we're actually going to do is just call it again. Yeah. Gonna do something like this. So basically we're just returning the directory entry structure that we should, but we're getting it from the original libc function. So again, the very first call to it, you know, we'll call the original libc read directory function, and it will fill in our directory entry structure. Make sure it's not null, and then we'll check the name of the structure, and if it's actually /, etc. ld_so.preload, what we do is we just run it again. So we're skipping it. We're basically saying, you know what, don't report this to the user, don't report this file exists, and just get the next file and then return. If it's not our file, not our secret file or whatever, or ld preload, sorry, it just returns the structure because that's okay. So let's see if that works. I don't know. I didn't really look ahead here, so I'm not too sure. Didn't plan this out very well. Oops, I don't know why I'm doing that. Whoops. We've got to include drn.h, compile it. Okay, I'm going to export it. Actually, first let's check. Is it? Make sure it's there. It's not. Am I exported here? I don't even know. Yeah. Okay. So it's there. Now let's set up our preload variable. Now we check it. It's not there. And now if I do a directory listing of the whole directory, hopefully it's hidden. But again, I don't know, because I kind of just do that on the fly. It's not. What am I doing wrong there? Let's see. Oh, you know what? It's actually not the full path. Because we're inside the directory. It's going to be like this. It's going to be just a file name. So let's compile that. Good. Now, where am I at? Now it's gone. That's the, I mistyped now, don't be mistaken, it's not LD preload. And if I unload it, it's back. So now it works as you'd expect. Now it works when you just stat it. So again, if you're doing ls of just like this, ld.so.preload, what ls is doing is it's just calling stat on the function. So that's why we've got to actually backdoor stat. And then if you actually list the directory contents, what ls does is it calls redirectory. And so we've also got to do Trojan redirectory so that we detect that file inside the directory and then handle that issue as well. Alright, so I know I kind of bumbled around on here as I was doing it. I should have probably wrote the code first, but figured it's probably better that you guys learn if you kind of see how I write it myself. And I kind of already know what I'm doing a little bit in terms of what I want to write. But, see, like I didn't even realize, when I'm looking at Trojan or, backdooring redirectory, I didn't even realize, in my head I'm thinking it returns, some kind of integer value, but no, it actually just returns a directory entry, a structure, that data type. So it's a little different in that, all we do is we just call it again, basically bypassing the output of our file. So let me go over the code real quick for this, because I know I wasn't very clear. Whenever you're doing an ls on a directory, ls itself will call something called read dir. And what that does is it will return to ls a directory entry structure, which is this, for every file name in that directory. So all we're doing is, again, we're writing our own read directory. Then we're going to grab the pointer to the real read directory for libc. We're going to call that and have it fill in a directory entry structure that we give to it. We're going to make sure that it's not null. And then we're just checking the file name for what we want to hide. And then if it is, that file name, all we're doing is we're saying, okay, read the next file. Basically just skipping the output. So ls, will never get that. It'll never return to ls because we basically read it and we're not going to return that structure. So if it's not our file, return a structure as normal because that's fine. It's a file that we can allow to be read. And again, real quickly with stat, remember that Lstat is a wrapper to all the other the three other stat functions. And all we're doing there is we're checking the file name to see if it's statting the file name that we're interested in, and if it is, we're returning enoent returning -1 and setting error node to enoent. Look at the difference. Remember the difference is here the file name is just the file name. It's not the full path, whereas stat is the full path. Same thing with open. Open what we're doing is we're using the /proc interface, looking for any kind of access to a certain PID, and if it tries to access that PID, error node sets to ent and return -1. Now again, remember this code. It's actually really bad. Most of these calls that I'm doing here, like calls to retrieve a pointer for libc. I mean, this void star p should just be one declaration up here, and then I should just check if it's null or not, and then call dl open if it's null. So because what's happening is every time read directory is called, I'm doing the same call, which I don't need to do over and over and over again. This doesn't really matter for you guys, but just a heads up. Hopefully you guys understood this a little bit. I know it was really jumbled and long, but look forward for my next episode, which will be a a little bit more stealthy, you're going to look into Linux kernel module rootkits, and where we're actually going to be able, in kernel space, modifying kernel structures and trying to you know, backdoor the system from kernel, in actual kernel memory. So that's the stealthiest we can get. It's as low levels we can get, and I believe it's what most people probably use nowadays. So thanks for watching, and have a good day.